For one final special named ring. In this case, we're going to define a Euclidean domain. Now, all of our special named rings, like a UFD or a PID or an integral domain, come from thinking about a ring that we're comfortable with, like the integers or a polynomial ring, and seeing what properties hold there and trying to abstract them. So, for example, in the integer ring, Z, you can factor each integer into a product of primes. So that's a really convenient property. So we abstract that and define a unique factorization domain where you could take any element in a UFD and write it as a product of irreducibles. Or if you have polynomials over a field, then every ideal is principal. So we generalize that idea and think of a principal ideal domain. Well, this is our final kind of ring that's defined by abstracting properties that we know and love from other comfortable rings, this time a Euclidean domain. And the idea is, if you have integers or polynomials, you could do division. You could define a Euclidean algorithm to find greatest common divisor. So we abstract that idea to arbitrary rings in the following way. So we start with the integral domain D, and it's a Euclidean domain if there's a function v, this is called a valuation function, that takes elements in your ring and assigns them to non-negative integers such that two properties hold. First, the value of a has to be less than or equal to the value of a times b for every non-zero a and b. And two, if you take an a in the ring and a non-zero b in the ring, then you could find a q and an r, like a quotient and a remainder, that satisfy this division. A is qb plus r. And this r, this remainder term, either has to be 0 or have a smaller value than b, what you're dividing by. So this is an abstraction of what you need to do division, what you need to do the Euclidean algorithm. So that's why it's a Euclidean domain. So let's see some examples. The integers are a Euclidean domain because you can do this division. What is the valuation function? Well, in this case, the valuation function is the function that sends an integer n to its absolute value. And you could check that property 1 is true because z contains no numbers smaller than 1 in absolute value. So when you multiply, it only has to get bigger. And 2, we have the division algorithm in the integers. Similarly, if f is a field, then the polynomials over that field are a Euclidean domain. The valuation function is sending a function to its degree. And we've seen before in our studies about polynomials that when you multiply two polynomials together, the degree can only increase. And we've even done division with polynomials. Here's another example of a Euclidean domain. The Gaussian integers, z adjoined I. The valuation function here is the function which sends a plus bi to a squared plus b squared. You might be tempted to take complex magnitude here, but if you take complex magnitude, then it's not guaranteed that you're going to get an integer out. So we don't take complex magnitude. We don't take the square root, just so that we get an integer. Now, it's not obvious right away that this valuation function on the Gaussian integers satisfies property 2. I'm not going to check the details in this video, but you can look in the text and they show you that this is indeed a valid valuation function on the Gaussian integers. So what I'd like to do instead in this video is prove the following theorem. A Euclidean domain D is a PID, a principal ideal domain. Remember, the definition of principal ideal domain is that any ideal in your ring is principal and can be generated by a single element. So here's the proof. I want to show something's a PID, so I start with an ideal. So let I be an ideal. And I need to come up with a single element that generates I. So here's how I'm going to do it. Take a B in I such that the value VB is minimum. So look at all the elements in your ideal I and find one of them that has a minimum value, valuation. Then take any other element A in your ideal. There are a Q and an R such that A is QB plus R. That's in the definition of a Euclidean domain. That's the whole reason we define a Euclidean domain. It's so that we can do this division right here. Okay. Now, this R, this remainder, either has to be 0 or has to satisfy the value being less than that of B. Okay, so R is either 0 or the value of R is less than the value of B. But I claim that this second condition actually can't happen. Why? Since R you can rewrite as A minus QB is in my ideal, because A is in my ideal, B is in my ideal, so QB is in my ideal. Therefore, the difference of these two is in the ideal. Since R is in the ideal, this cannot happen. This cannot happen. R has to equal 0. R has to be 0. So, thus, A is Q times B, and what we've just shown is that if you take any element A in the ideal, it's a multiple of B. So the ideal is actually generated by B. Now looking back in the proof, I realize I should have taken B to be non-zero in the ideal. That's something maybe I should have set up here, because if B is 0 itself, then this argument doesn't quite work, but anyway, we're fine. So what we have here is a Euclidean domain being a PID. A PID, as we've seen before, is a UFD, and all of these are integral domains. So I'd like to end this video by showing you one more Venn diagram type thing about our recent studies in integral domains. So here we have commutative rings. Our rings have unity 1, and as a subset, integral domains. UFDs are a subset of integral domains, PIDs are a subset of UFDs, and Euclidean domains are a subset of PIDs. So allow me to fill in elements in each one of these categories. So a Euclidean domain, as we've just seen, includes polynomials with coefficients in some field, integers, and even the Gaussian integers. These are all Euclidean domains. A PID that's not a Euclidean domain, that could be the reals. So I'm going to look at polynomials in x and y with real coefficients, and I'm going to mod out. I'm going to look at the factor group modded out by x squared plus y squared plus 1. And I'm not going to prove it, but this is an example of a PID that cannot be a Euclidean domain. Similarly, another kind of bizarre example are the rationals where I adjoin the square root of 19i. Now both of these are kind of tricky to prove, that you cannot define a valuation function, that you cannot have a Euclidean domain. So I'm going to omit the proofs, but just know that these examples exist and they're a little bit exotic. Examples of UFDs that are not PIDs include polynomials in two variables. We've seen that as an example before. And you could even do polynomials over the integers, polynomials that are not over a field. So zx, we've also seen an example in our past where this is not a PID. And lastly, maybe let's write down an integral domain that's not any of these other special named rings. We've seen an example where you have the integers adjoin root 5i. Okay, wonderful.